Thank you so much for inviting me to give this talk. So this talk would be on the nuclear experiment and theory side connecting to neutron stars. I would like to discuss some recent progress and some challenges in the nuclear equation of state coming from neutron skins and neutron stars. Essentially, there is 18 orders of magnitude between a finite nucleus and a neutron star in size. So you would like to build a density ladder taking from the finite nucleus all the way to neutron stars. And how well we do so, it depends on the interpretation of the models that we use, and that's what we are going to do. So as once very famously put by Lev Landau, neutron stars are essentially one giant nuclei or nucleus. In this case, of course, you have 57 orders of magnitude difference in their masses, but they share very similar densities. So the average density of a nucleus is about 7.7 saturation density, what we call, but the average density of a neutron star depends on the mass. Nevertheless, it's in the orders of saturation density. The two are vastly different in their structure, but yet they share the same physics, the physics of strong interaction, and that's what we are all trying to identify in this workshop as well. So the nuclei usually are supported by the surface tension. So the formation of the size of the nucleus depends on how strong is the surface tension, but the formation of the neutron star depends on the gravity. So how strong is the gravity? Now, if I plot the density of the nucleus as a function of radial distance for let's say for lead, I get what we call almost identical density in the central regions. We call it saturation density. This density is very well known, or at least known to a very high accuracy. And it turns out that this density is also almost identical for all nuclei. So if you take, for example, calcium-48 or any tin-132, you would find a very similar density in the central regions. And however, for neutron stars, the density depends on the mass of the star that you want to predict. For example, the larger the mass is, the central densities can go to several times saturation density, to up to 6, 7 saturation density, for example, for maximum mass stars. And since they are treated with the same equation of state, or they're governed with the same equation of state, now it's important to see what kind of an equation of state would give what kind of a size of the nucleus of a neutron stars. And it turns out the pressure determines the size of the nuclei, both the nuclei and the neutron star. For example, if the pressure is very stiff, we call it stiff equation of state, then you get a large nucleus. And if the pressure is, of course, stiff, you get a very large neutron star radius. So there is one-to-one correspondence in that sense. Of course, the species differ. One has neutrons and protons, and in the minimal model, you have at least electrons and neutrons in addition to neutrons and protons in beta equilibrium. And we solve, again, different structure equations. One is relativistic nuclear structure, the other is general relativistic stellar structure. Even though the equation of state for nuclei are very well known as we think so, it turns out that one particular sector of the nuclear interaction is not well understood. We call it as a vector sector of the nuclear interaction, and that's not very well constrained. So models that very well predict the properties of finite nuclei then predict a vast difference neutron star radii predictions, for example, or maybe tidal polarizability or moments of inertia, etc. These differences arise from one particular sector, as I mentioned, is called as a vector sector, and that's we don't understand. And the primary reason for that is that nuclear experimental data that we have are all close to a symmetric nuclear matter. So there are very few experimental data from neutron-rich matter, and as a result, these models predict very vast or differences in neutron star radii. And that's the main reason of this talk. And this slide was shown earlier also on Monday by Professor Gulminelli. And I just wanted to show it again because I want to concentrate on one particular property called the nuclear symmetry energy here. Essentially, the equation of state can be written into two terms. One is the symmetric nuclear matter, where neutrons and protons are equal, and one that tells how much energy is needed to convert protons into neutrons, and or vice versa. And that coefficient we call as a symmetry energy. And the density dependence of this symmetry energy is the most uncertain part of the equation of state. In fact, these isovector sectors uncertainty can be attributed to this one particular quantity called the density dependence of the symmetry energy. And that further can be expanded and often is expanded in Taylor expansion around nuclear saturation density, and the value of the symmetry energy, the slope of it, and the compression modulus of that is often talked about in the discussions. And I will also concentrate on one of these called the slope of the symmetry energy. Also, yesterday you have seen a talk by Melissa Mendes on the role of the slope of symmetry energy on the neutron star neutrino cooling. And this slide was also shown this morning by Tim on essentially saying that the symmetry energy is essentially the difference between the pure neutral matter and symmetric nuclear matter equation of state. Since symmetric nuclear matter is saturated at saturation density, and which means the pressure is zero at that point, the pressure of pure neutral matter is then identical or almost identical to the pressure of the symmetry energy. So knowing the pressure of the symmetry energy tells me what will be the pressure of pure neutral matter, which is very important for neutron star structure, because it's the pressure of pure neutral matter essentially that determines the size and all other size sensitive properties of neutron stars. Now, how well do we know the equation of state of symmetric nuclear matter? It turns out that nuclear masses constrain the binding energy at saturation to less than 5% level. In fact, it dates back almost to 1935, and we know very well the nuclear binding energies. So that coefficient is taken care of, E0. But Jan monopole resonances and other breathing modes can also constrain the compression modulus of the symmetric nuclear matter that K0 is also taken care of. And it turns out that the high density equation of state of a symmetric nuclear matter can also be constrained by means of heavy ion collisions. For example, this data was obtained almost 20 years ago by flow analysis, and we have a constraint on the high density component of the equation of state as well for symmetric nuclear matter. So a freak, for example, can help identify the equation of state at high densities. Now, more or less, we do know the equation of state of symmetric nuclear matter. And then when we predict our models for the symmetry energy or for the equation of state of pure neutral matter, then we see vast differences in the model predictions. And that's the reason that we have different radii that you've seen in the first slide. So there are some recent, of course, theoretical progresses especially from chiral EFT and some quantum Monte Carlo calculations that say that more or less there is some agreement on what the pressure of the equation of state of pure neutral matter should be. But nevertheless, these are purely theoretical in nature. So we need experimental data to constrain the equation of state at these densities. There is some agreement at subsaturation density, and that's because the average density of a nucleus is about 0.7 nuclear saturation, and as a result, the binding energies actually fix the symmetry energy at these densities. But it's the pressure of it that's very important that we need to know, and that pressure is not very well known. And in this talk, I would like to concentrate on one isovector observable. It's the neutron scheme. Essentially, consider the lead-208 nucleus. It has got 82 protons and 126 neutrons. The difference is 44 neutrons. And the question is, where do these neutrons distribute themselves? Where are they located in the lead isotope? It turns out that the neutrons' pressures are slightly larger than the proton pressure. As a result, they push these 44 neutrons out to the outer layers of the nucleus, and the very outmost region of the nucleus of lead is made of pure neutron matter. We call that region as a neutron skin. And the size of the neutron skin is essentially very much correlated to the pressure of pure neutron matter. If the pressure is very large, the size will be also very large. And the pressure is small, the size will also be small. And this was actually determined by P-Rex experiment in 2011, and most recently updated in 2021. They measured very accurately the neutron radius of lead isotopes. Actually, almost like 2 weeks ago or a week and a half ago, C-REX experiment, which is a calcium experiment, also measured the neutron skin of calcium-48, which I will discuss in the last slide. Now, the neutron skin, we say that is strongly correlated with the pressure. So you can see the pressure is actually basically the slope of the symmetry energy. So the neutron skin is strongly correlated with the slope of the symmetry energy, as this was shown by Rocamazza, for example, almost 10 years ago. And this strong correlation also can be extrapolated to neutron stars. And we found that the neutron skin is actually strongly correlated to a host of neutron star observables, such as neutron star radii, moments of inertia, and moment of inertia of the crust, for example. That was very important for the glitches talk that we heard this morning. And of course, through tidal polarizability and radii as well. Now, this correlation can be understood very easily because the pure neutron matter tries to push against surface tension and generates a neutron skin. And this same pressure, or at least similar pressure, pushes against gravity, and therefore the neutron star radius is determined. So the larger is the neutron skin, the larger would be the neutron star radius. And how do we determine it is done by using the so-called parity violating experiment. The experiment essentially does the following. First of all, the proton form factors or the charge form factors have been known with very high accuracy since the late 1950s, for example. That's because electrons are essentially sensitive to protons only because they see the charged particles, and they are almost insensitive to neutron distribution. So neutron distributions or neutron form factors were not known up until very recently. In fact, it's still not very well known. This experiment uses the parity violating asymmetric parameter. It measures that. So it uses the parity violation. Parity is not conserved in weak interactions. So by calculating the difference in the right-handed and left-handed differential cross-sections, we can determine the parity violating asymmetry, which is sensitive to neutron form factors, as you can see in here, because the proton form factors is very well known, and this difference, the Weinberg angle 1 minus 4 sine squared, is almost 0. So essentially A is very sensitive to Fn. Measuring A, I know the neutron form factor. Knowing neutron form factor, I would know neutron densities. Of course, the experiment is very hard to do, so essentially it's done at 1q momentum transfer, and we get the neutron radius with very high accuracy. That was the goal, and it was done in JLab last year and 2 years ago, actually, and was reported last year, but also this year. And there is a plan at Mainz to do the same measurements with even higher accuracy. Now, what did the experiment tell us? The experiment told us that the parity violating asymmetry is in this range, is shaded blue here, because of the strong correlation that you can see, and with the model predictions, of course, and we can predict that the neutron skin has to be somewhere between these two values, and the central values being 0.283 plus minus 0.071. Such a large neutron skin was not kind of expected by other experimental results, primarily because every other predictions told that the neutron skin should be smaller. So it was surprising that the neutron skin of lead was very large. And I should note that the large neutron skin also would tell a large slope of the symmetry energy, because there is a correlation between them, as you can see here. The actual correlation is strongest at subsaturation density, as you mentioned earlier, mainly because it's the subsaturation symmetry energy that that is the average symmetry or energy of the nuclei. So nevertheless, we can get the slope of the symmetry energy with high uncertainty, of course, plus minus 37 MeV, but it's very large. The central value is very large. Now, it doesn't agree with other predictions, as you can see. So this was surprising. So there is some tension with other experimental data, especially electric dipole polarizability, a very precise experiment that was done, and some other theoretical predictions. Now, the tension grew, and of course, you can see this tension in this JL plot that is often quoted. In fact, this paper had been this figure had been circulating around. There is a concordance region. There is an agreement region that people often quote. They say that the symmetry energy, the density slope of the symmetry energy has to be between, for example, 40 and 60 MeV, because everybody agrees in that. As you can see, the P-Rex experiment certainly does not agree with that region. So maybe the concordance region should be taken with a caution, and we should really see whether our models can simultaneously describe all of these experiments at the same time. So there is a strong tension between this P-Rex2 result and other experimental results. Now, reference this Reinhardt et al. Immediately put the P-Rex data at the same time, and they described the also electric dipole polarizability. And they found that the tension is very strong indeed, and the only overlapping region would tell that the slope of the symmetry energy is somewhere between 54 with plus minus 8 MeV, meaning that there is a very tiny region in which P-Rex2 experiment and the electric dipole polarizability experiment would agree on. So in some sense, it's good because we got the symmetry energy, the slope of symmetry energy. In other sense, it tells that maybe our models are too rigid or too tight. Now, another analysis was done by Yu et al. Almost followed at the same time. They included, besides the gel monopole resonances from experiment and heavy ion collision data, they also included observation of maximum mass of a neutron star and nicer radius measurements, etc. And they found similar but slightly looser constraint. They found that the symmetry energy should be below 73 MeV. Again, P-Rex is above 69 MeV. So again, slightly looser constraint or maybe higher constraint, but at least agreeing with that. So the tension exists. That's what I wanted to say. Now, if just taking the P-Rex2 results alone and trying to predict what would it imply on the particle composition of a neutron star, you would see that, of course, the higher slope or the large slope of the symmetry energy essentially means that the symmetry energy itself, the value of it at higher densities, are much larger than its at saturation density, because the slope is large, so the symmetry energy is very large, which means that it's very difficult to convert protons to neutrons, and therefore the neutron star will be less neutron-rich, so it will have a chunk of proton fractions. But a large proton fraction allows the neutron star to cool down in what we call a direct Ulker process. So the direct Ulker process is a process in which you already know it, but I just wanted to mention that neutrons can get converted to protons and electrons, and as a result, a neutrino, anti-neutrino in this case, would run away and getting all the energy and cooling down the neutron stars. This talk was given yesterday by Melissa on the role of the symmetry energy or the dependence of the symmetry energy on coolings of neutron stars. So far, by the way, I should say that there are not many cold stars, which means if we trust the P-Rex2 result alone, let's say if we just believe that the symmetry energy is larger than that, almost every star in the universe, or most of the stars, as you can see here, must undergo direct Ulker, which means every star that you should see should be very cold. In fact, you shouldn't be seeing them because they are too cold to observe. Now, but we only have a few of them, which means either the symmetry energy, of course, dependence of symmetry energy is very large, but the neutrino emissivity is suppressed by nucleon pairing, or maybe they are small, but then it would be inconsistent with P-Rex2 data, so that something is wrong with the data, you can say, or maybe there are some phase transitions that's going on in the central regions of the neutron stars. So this is a very interesting case study. And again, if you take the P-Rex2 at the face value and predict the tidal polarizabilities and neutron stars, as you can see here, we get tidal polarizabilities. This blue allowed region is the region where it agrees with P-Rex and also the nicer data. Then you can see that the radius should be between 13 and 14 kilometers. So should be tidal polarizability larger than 642 and smaller than 955. We can also impose a limit on the neutron skin of lead, so from above 0.31. Now, what if the tidal polarizability is smaller than 600? So if that's the case, then the equation of state has to be soft at higher density where the P-Rex cannot probe it. So the nuclear experiments cannot probe any equation of state at higher density. So we expect the equation of state should be softer, somewhere in twice saturation density, so that we can get a smaller tidal polarizability. And there was recently discovered this particular binary system in which one of them was very small. It is a 2.6 solar mass compact object. The question is now, of course, if it is a neutron star, for example, can we come up with a model that agrees with all experimental data and also observational data? Or the question is whether this is a neutron star or a black hole. Now, it's possible to come up with a model. In fact, we came up with what we call Big Apple model. The Big Apple model can describe the properties of fine nuclei to a very high accuracy. So we get a saturation density, binding energies. Not only that, but we get also binding energies and charge rate of all nuclei very well, to less than 1% accuracy. And however, it suggests that the slope of the symmetric energy has to be about 40 MeV, so which is much, much smaller than what the P-Rex2 had suggested. And as you can see in this plot, mass versus radius plot, the red plot is essentially the Big Apple equation of state. It agrees very well with the nicer data. It actually goes straight through the middle of it, agrees with other Boswine's predictions, and also agrees with the 2.6 solar mass. So it's a very good model that you can come up with, and also gives a tidal polarizability of 717. So you would think that there is no problem with this kind of a model. However, if you look into the details of it, it turns out that this model or this equation of state is very soft at intermediate densities, but is very stiff at high densities. Such stiffness is not in agreement with the flow analysis. So the flow analysis constraint is this blue box, but the red data goes much above it. It's a logarithmic plot, so I have to mention it. So given that there is a very strong tension with this flow data, and also there is a slightly slight disagreement with the P-Rex2. In fact, it agrees with P-Rex2 at 2 sigma level, but with the original P-Rex, it agrees kind of. So with this kind of tensions, we can only assume that this 2.6 solar mass object is not a neutron star, perhaps a black hole, or maybe some other strong field regime of gravity should be understood well, because general relativity, we do know it works for most of neutron stars, but at these high densities, other models of gravity may be in effect as well. So in this last slide that I want to concentrate on the very recent, like 2 weeks ago, published result from C-Rex experiment. The C-Rex experiment came and got us all, so we were surprised with the result that they came up with, and turns out that once the experiment was done, the neutral form factor was obtained, the analysis was done. So it turns out that the neutron skin of calcium and lead is just predicted by models, and these are experimental results that you can see. So the experimental result is shown with red. For neutron skin of calcium, it's about 0.12 Fermi, and this is a P-Rex result, 0.28 plus minus 0.7. Now, none of the models, this is a correlation of the models, none of the models agree with this 67% or 90%. I mean, they agree in the 90% region, but none of the models actually can describe both of them simultaneously. Now, that is a very interesting, because if you take the slope of the symmetric energy very small, yes, you can describe calcium, but you cannot describe lead. But if you take it too large, then you get the lead very well described, but not calcium. So perhaps we do not understand the isovector sector very well, and in fact, we would suggest that everyone, I mean, either non-relativistic or relativistic models, they should expand or try to expand their isovector sector, and we must revisit this sector to just understand how the symmetric energy even behaves as subsaturation density, so that we can get both of them accurately. Now, I can only speculate that once it's possible, in fact, with, as I say, that with a few more parameters, I can even fit an elephant. Yes, it's possible to get both of them correctly. I only can speculate that this tension will only grow when we try to extrapolate them to neutron star matter or neutron star observations. So just to summarize, some recent experimental data from neutron skis put some tight constraints on the density-dependent symmetry energy below saturations. But when you combine this with observational data, you get sometimes a strong tension. These tensions can in principle be improved, and one can use then a density ladder from nuclei all the way to neutron stars. But to improve the current models, we need new features in isovector sector of the nuclear interactions. And I think it's very important, especially given the recent data from calcium experiments. So I stop here and take questions.